Welcome to week number 4 for ECE 401 Senior Design 1. In this lecture, we're going to look at using CircuitLab and OpAmp, kind of a review of Circuits 1, Circuits 2, some electronics. So CircuitLab is a tool that we use in our program. It's a really nice circuit simulator. It's a graphical interface that's very similar to Spice or PSpice if you've seen those. The graphical front end makes CircuitLab exceedingly easy to use. It's basically drag and drop. What CircuitLab does is it lets you check your design using a nonlinear circuit simulator. Your hand calculations typically make approximations, such as assuming ideal diodes, meaning a 0.7 volt drop, assuming when a transistor saturates, the voltage drop, collector to emitter is 0.2 volts, things like that. Things that are almost true, but not quite. Makes calculations a whole lot easier. Well, in CircuitLab, it uses a more accurate nonlinear model. That way you can check to see, will the circuit work in practice? What CircuitLab also lets you do is it lets you adjust your circuit if necessary. If I'm trying to get the current through the diodes to be 20 milliamps or 10 milliamps, and it's a little bit off, I can adjust the resistors just by double-clicking, changing the value, trying to get a value that's closer. Once your design is finalized, you can then start building the breadboard. Now, CircuitLab is useful in a large number of classes. In Circuits 1, Circuits 2, you build RLC circuits with CircuitLab for DC signals or AC signals. In 275, Digital System Design, you have the AND gates, OR gates, flip-flops, binary signals. In electronics, you add in op amps, diodes, transistors, MOSFETs. There's also a section for control systems with transfer functions, summing junctions, stuff like that. Basically, CircuitLab is just pretty darn useful. To use CircuitLab, there's a couple of ways you can do that. You can use the trial version. The problem with the trial version is if you don't register, if you use the trial version, you're limited to half hour per session and you can't save your work. If you do register, then you can basically save your files. You have unlimited number of sessions. You can share files. For registering, there's two versions. If you register using your NDSU email address, and this has to be ndsu.edu. There's also NDUS. NDUS is the North Dakota University System. That includes UND, Bismarck State, Williston State. There's NDSU, looks almost the same. NDUS probably doesn't work. Again, NDSU only pays for the NDSU students, not everyone else. You'll need to use your NDSU email address. You can also get your own version of CircuitLab so that when you graduate, you still have all your files. That costs you $24 a year. But you have your files after you graduate. In terms of op amps, one of the requirements for Senior Design 1 is you have to include an integrated circuit. That could usually be an op amp, a 555 timer, a Raspberry Pi Pico, your pick. Op amps are just really useful. They're devices that can do all sorts of things, such as comparators, Schmitt triggers, half-wave, full-wave rectifiers, envelope detectors, amplifiers, filters, and so on. They're just darn useful. In CircuitLab, there are two types of op-amp circuits available. There's an op-amp without plus and minus power, and there's one where you do give it plus-minus power. That really depends upon how you want to use it. If the power supply doesn't matter, such as for analog circuits, you don't have to specify them. If you do care about the power supplies, like digital circuits, then you do have to specify them. Typically for analog circuits, I want to output a sine wave. So here's the signal coming out to my speaker. I'll have my plus power supply, the minus power supply. As long as these exceed the range that I need, what these are doesn't matter. That's what this symbol's for. If, assuming my power supply is sufficiently large range that I don't clip, I don't care what it is. In contrast, for digital circuits, I'm going to slam high, slam low. I need to know what the logic levels are, like 0 volts and 5 volts. That's what these tell the op amp. The Plus side says that when I rail high, what does high mean? In this case, high is 5 volts. When I rail low, what does low mean? In this case, it means 0 volts. You have to specify that. The pinouts for an op amp are fairly standard. There are, for example, the MCP602 in your kit has dual op amps. Pin 4 is ground. Pin 8 is power. That's anything between 2.7 and 6 volts. For the R class, that'll be 5 volts DC. The LM358 is more for an analog output. It has plus-minus inputs. This will be like minus 1.5 to minus 20 volts, plus 1.5 to plus 20 volts. Otherwise, you have 2 op amps in each package. Here's the first one, here's the second one. They put the plus and minus, or the output and minus, close to each other because a very common op amp to use is a voltage follower. Short these 2 pins, and if I apply a sine wave in, I should have a sine wave out. That's a buffer. The parameters for op amp depends upon the op amp that you're using. The input impedance for the 2 op amps that we're using are exceedingly large. Basically, you can assume for an op amp, the current coming in is basically 0. The output current, op amps are limited. The ones we're using can handle either 25 or 40 milliamps out, either source or sink. There's sourcing, there's sinking. The op amp is a differential amplifier. The output gain is a large gain times the difference between V plus and V minus. That's the differential gain. In theory, it's infinite. In practice, it's not quite infinity. What this means is, I can take this number, if the output is 1 volt, and I'm not clipping, that means the difference between these is 1 divided by the gain, 2 microvolts. In theory, the gain is infinite, so this difference is 0. In practice, it's not exactly 0. I need a small difference to drive the output because the gain is finite. But typically that's so large, this is so small, I can assume roughly that V plus equals V minus for analog circuits. The common mode gain is if V plus and V minus go up and down together, the output should be 0, because ideally this is some gain times V plus minus V minus. If V plus and V minus go up and down together, this cancels. In practice, if they go up and down together, there is a slight change in the output. That's the common mode gain. Should be 0. It's not quite 0, but pretty close. The slew rate limit is if you have a sine wave going out that looks like this, that's typically a slew rate limit. The op amps have an upper bandwidth. If I try to make the output change too fast, my sine waves become triangle waves. That's your slew rate. The output can only change by 2.3 volts per microsecond for 602. The gain bandwidth product says that I can have a gain of 1 out to 2.8 megahertz, gain of 10 out to 280 kilohertz, gain of 100 out to 28 kilohertz. Basically, this says op amps have a gain, keep the gain less than 100, and I'm good to 28 kilohertz, good to the audio range, and the operating range and temperature and cost. Now for the op amps, typically in electronics, we use these 294 LM358 because they're cheap. If I need digital circuitry, I'll use the 602. That's the 0 to 5 volt operation. These use plus minus for analog circuits, digital circuits. In terms of op amp circuits, there's a whole bunch you can use. Op amp circuits are really like Lego blocks. If I have a certain function, I will just grab the circuit and plug it in. If I want a comparator, the input-output voltage looks like this. It's either greater than or less than, true or false, black or white. That's a comparator. In this case, if X is greater than 1.5 volts, the output is true, and true in this case is 5 volts. If it's less than 1.5 volts, it's false, it's 0 volts, this guy. Schmidt trigger has this type of characteristic. The on voltage is different than the op voltage. If the on voltage is higher than the op voltage, I use this configuration. If the on voltage is less than the op voltage, I use this configuration. This is one of the few circuits you're ever going to see that has positive feedback. The positive feedback makes it unstable, which is what I want. I want the output to either slam high, 5 volts, or slam low, 0 volts. I don't ever want to operate in the middle. For example, suppose I want to build a night light. That's a circuit that'll turn on when the room is dark, turn off when the room is light. Well, to do that, I first have to find what is light, what is dark. What I could use is a light sensor. Suppose the light sensor is 3 kilo ohms when the light is on, 10 kilo ohms when when the room is dark. To come up with a circuit that outputs 0 volts, 5 volts, I'll first convert this to a voltage. So I'll take my resistor, like so, my light sensor, build a voltage divider out of it with a 5K resistor. What that does, that converts resistance to voltage. So I want the voltage, the light to turn off at this voltage, turn on at this voltage. So I could pick a voltage in between, threshold like 2.5 volts, turn on and off at 2.5 volts. In that case, this would be my circuit. Here's my 2.5 volts, my reference. Here's my light sensor. The way light sensors work, as lux goes up, the resistance goes down. So when it's really, really bright, R goes to 0, X goes to 0. A is greater than X when it's really bright. This is 5 volts when the room is really bright. So this is a circuit that will output logic 1 when the light is on, 0 when the light is off. And to generate 2.5 volts, I can just use the voltage divider. An example of that is, suppose I want to build a circuit that counts on a Raspberry Pi Pico or RP0. What I would do is, here's my RP2040 Raspberry Pi Pico, taking the output of the comparator. That's what this circuit does. So here is the Raspberry Pi Pico, it's actually RP2040. Here's my comparator, there's my light sensor, and here's my 2.5 volt source. I'm actually using a potentiometer for that. That lets me adjust the voltage. This is the output voltage. It goes to your op amp, to pin 8 on the 2040. To see if that works, what I could do is write a little test code. I'll make this pin an input with a pull-up resistor. If I read logic 0 or logic 1, I'll display it. So here's what that looks like. So here I've got a shadow going over it. There's my shadow as a 0. Take my finger away. Logic 1 is no shadow. Logic 0 is dark. Light, dark. And the other one's a push button. When I hit the button, I get logic 0, logic 1. What the push button does is it just has this pin tied to ground through the push button. To push the button, these are shorted to ground. Open, it's not connected. If I want to use the NeoPixel on the Raspberry Pi, that'd be this code. The same code as before. If I hold the button down, I'll make the light red. Hold this button down, I'll make it green. Display it. So what that looks like, running that program, if I put a shadow over it, that turns green, so here's my shadow. If I hit the button, that turns red. And both together is red and green, yellow. Third case, let's build a counter. So to build a counter, what I'm going to look for is a falling edge. If I see a falling edge, that was the button was pushed. So what I'm going to do is look for the current value of the button, the previous value. If the current value was a 0 and the previous value was a 1, that was a count. And what that looks like is here's my count. So here's the counter on the light, 3, 4, 5, counter on the button. And if you zoom in, you can see button pushed, button release, button push, release, dark, light, dark, light. Now one problem with a comparator, if I bring my hand right on the edge, I'll get multiple counts. There you can see I'm getting multiple reads. What's happening is there's always noise on the signal. So if the signal does this, when it passes through my logic level, I'll get multiple reads. That's what happens with a comparator. In CircuitLab, I can check my design. Here's my 5-volt signal. That's my 2.5-volt reference. I'm going to have B3 be a sine wave that goes above and below 2.5 volts. So this has the DC offset and going up and down above and below 2.5 volts. What I want to see is the output is it switching between logic 1, logic 0 as X goes above and below 2.5 volts. And what that looks like is this. So this is the on voltage. When it goes below, that's off. When it goes above, it turns off. Goes below, it turns on. The reason it does that is it connected to the minus input. And notice V on equals V off. That's a comparator. If I add noise to the signal, I get chatter. To avoid the chatter, I can separate V off and V on. That's a Schmidt trigger. So let's have the on voltage be 2.4 volts, have the off voltage be 2.8 volts. The circuit that does that is a Schmidt trigger. That's a circuit with positive feedback. The way you do that is the on voltage is less than the off voltage, so connect to the minus input. The offset is the on voltage, and the gain is the slope. Output changes by 5 volts, as the input changes by 0.4, 12.5, make this 12.5 to 1. That gives you a Schmidt trigger. In CircuitLab, if I simulate that, again, here's a sine wave. It goes above and below the V on and V off. If I simulate it, what you'll notice is when I go below 2.4 volts, it turns on. When it goes above 2.8 volts, it turns off. So V on and V off are different. That's a Schmidt trigger. What a Schmidt trigger would do is that would avoid multiple counts. So like in this circuit, that's just a comparator. There are no resistors. There is no feedback. With that circuit, I get multiple reads, which you're seeing here. Oops, I stopped the program. There's 2 reads. There's a bunch of reads. If that's a comparator, make that a Schmidt trigger. I won't get the multiple reads. Okay, next, let's look at analog circuits. If I want to build amplifiers, op amps can be used for that as well. The simplest is Y equals X. The reason you might want to do this is the input impedance is typically like 4 gigaohms. The output for the op amps we're using can do like 25 milliamps. If I want to have a gain, there's a non-inverting amplifier. Here the gain is 1 plus R1 over R2. Kind of the way that works, this is a voltage divider. If these are the same, then with negative feedback, V plus equals V minus. If these are the same, V minus is 1/2 of Y. Therefore, Y is twice X. Or the gain is 1 plus R1 over R2. Inverting amplifier is this configuration. The gain is minus R1 over R2 times Vn. And the do-all everything is an instrumentation amplifier. This has a gain of R1 over R2 times the difference between A and B. This could be a non-inverting amplifier, inverting amplifier, a differential amplifier. Can do everything. The way you find the equations for op-amp circuits is you count the voltage nodes. In this case, I've got 1, 2, 3 voltage nodes. If I write 3 equations for 3 unknowns, I can solve. One equation is at the output that says that B plus equals B minus. The way that works is assume the output is something like 1 volt. If the gain is really, really large, like 100,000 or a million, the difference between B plus and B minus has to be very, very small. So essentially B plus equals B minus, and the limit as the gain goes to infinity, these have to be the same. Next equation, at B plus, the current left, current right adds to 0. That's right here. At B minus, the current left, current right adds to 0. 3 equations, 3 unknowns, do some algebra, and I get this. A current sensor. As an example, suppose I want to measure the current through a 1 ohm resistor. If the resistor is to ground, what I could do is have some current going through it. The voltage is I times R. The voltage is just current. Build a buffer circuit, and this will have Y is the current. So 1 amp is 1 volt. If one amplification, such as the 100 milliamps, becomes 3.3 volts, I want a gain of 33. This is an amplifier with a gain of 33 times X. Y is 33X. 100 milliamps is now 3.3 volts. In CircuitLab, I could check that design. Here's my circuit. Here's my sine wave coming in. Here's my amplifier. Let's just simulate a sine wave. This is 1 kilohertz. Period is 1 millisecond. Let's simulate it for 2 cycles, 2 milliseconds. Make the step size 1,000 times smaller. Plot X and Y. And what you see is that X is basically 0, no change. Well, very, very small. Here's the output. It's going plus or minus 3.3 volts, as you expect. And again, the reason for the 100 ohms is if this is a 1 volt sine wave, this is a 10 volt sine wave, the current goes plus minus 100 milliamps, should give me the 3.3 volts out. Second version. If my current sensing resistor is not to ground, I could use a differential amplifier. That's where this one's used. I'm going to convert current to voltage with a 0.1 ohm resistor. This is why they make 0.1 ohm resistors, in case you ever want to measure current. I'll amplify by 10, so 1 volt is 1 amp. In CircuitLab, I could check that. Let's just kind of show that this is not tied to ground. I've got 10 ohms split up evenly between R1 and R13, and a sine wave, 10 volt source. This is my 0.1 ohm current sensing resistor. Here's my gain of 10 amplifier. And what I see is 10 volts at 10 ohms is 1 amp. The output is swinging between plus minus 1. There's my 1 amp that I'm measuring. 1 volt is 1 amp. A third use of op amps is for filters. I can build filters with inductors, resistors, capacitors, but inductors are really poor. They have a lot of resistance, they have crosstalk. Circuits work a lot better if I don't use inductors. With an op amp, I can avoid the use of inductors. The circuit I use depends upon the filter that I want. If I just want a DC block, this has a DC gain of 0. AC gain passes, that's this circuit. If I want to build a low-pass filter with real poles, here's a 2-stage low-pass filter. The corner is roughly 1 over R1C, 1 over R2C, and I need R2 to be much bigger than R1, like 10 times, with a gain. If I want a single pole, this has the pole and a gain. This has two poles with two complex poles. For example, suppose I want to build this circuit. I've got real poles, so I can use this circuit. Pick R1 and R2. R2 is 10 times bigger than R1. 1 over R1C is your first pole. 1 over R2C is your second pole. This is the gain. The DC gain of this circuit is 50 over 6. Pick this so the gain is 50 over 6. In CircuitLab, I could do a frequency sweep and show this is a low-pass filter. DC gain is 50 over 6. Here's the pole at 2, pole at 3, then drops off. If in contrast I wanted to have complex poles, that's a different circuit. In this case, 1 over RC is the amplitude of the pole, thus square root of 50, or 7.07. Pick R, solve for C. The angle of the pole tells you the gain. Let's see. It's 3 minus K is 2 times the cosine of the angle. K is 1 plus this ratio. Tells me K is 2.717. This ratio is 1 minus that, 1.717 to 1. That gives you this filter. The DC gain is a little bit off. I could add another stage to fix the DC gain or just live with it. So technically this has a DC gain of 2.7. This isn't actually Y. This is 2.7 times Y. DC gain is 2.7. In CircuitLab, I could simulate it, build that circuit, do a frequency sweep. This is the complex pole. It's got a resonance at the complex part of your pole, about 7 radians per second. And that's kind of some idea in homework 4. In homework 4, that's due week number 8, is simulate the major sections of your circuit using CircuitLab. Typically you do the DC analysis, check your currents and voltages, do the transient response if applicable, simulate the waveforms if you're using a 555 timer, check the resulting frequency and duty cycle, compare the simulation results versus your calculations, checking to see are your calculations correct. If they're incorrect, like the current through your diodes isn't 20 milliamps, make some adjustments. Also note the test points. These are the signals that you use to validate that your design works. Note what signals you're looking at, note what the results are. You're going to need those later when you get to your breadboard, and you want to check does your breadboard work. So that's kind of a quick summary of op amps. This is stuff that you cover in Circuits 1, Circuits 2, and Electronics. Op amps are really kind of like Lego blocks. You built up a circuit by piecing together op amp circuits with different functions. One set of functions are for digital op amps, or digital circuits. Another set of circuits are for analog circuits. Another one's for filters. CircuitLab lets you check your design, meaning do the digital circuits output the correct voltages, do the amplifiers output a sine wave, when the input is a sine wave, put the correct amplitude, do filters have the desired gain versus frequency. And note that the op amp that you use depends upon the type of circuit. Typically, digital circuits use MCP602 op amps. Typically, analog circuits use LM2904 or LM358 op amps. And that's kind of the different circuits that you cover when you get to electronics, as well as circuits. The op amp that you use, the circuit that you use, depends upon the actual application. And that is lecture number 4 for ECE 401. If you need an op amp in your circuit, this is kind of a quick review of circuits and electronics.